Good afternoon, or at least it's afternoon for me. We're going to skip a couple of sections in the text and move to section 3.5 on resolving conflict. So first of all, don't get your hopes up. This is not going to tell you how to get along better with your roommate or significant other or whoever else you've been arguing with. This is the kind of conflict that you have when your friends are trying to get together and you're involved in 100 different activities, and friend number one is involved in 150 different activities, friend number two in 75 different activities, and you're just trying to find a time when you're all free to meet. Of course, a secretary in a corporation or the registrar in a university who's trying to schedule classes has exactly the same scenario. Various people want to be at the same activity, and they're not all available at the same time, and so you're trying to find a time that works for everyone. That's the kind of conflict resolution that we're talking about here. First of all, though, we're going to move to a apparently completely unrelated question, and then at the end you'll see how graph theory comes back and helps with this scheduling situation that I just mentioned. Here's the seemingly unrelated question. Here's a map of the United States, and we'd like to know how many different colors we need to print this map so that no two adjacent states are the same color. Of course, when you make a map with different political units like this, it's customary that different states that are adjacent have different colors, so you can easily tell them apart. Okay, well, we might just try something. Rather than using colors, I'm going to use different numbers. So maybe we make Georgia one color, and then because Florida is adjacent to Georgia, it would have to be a different color. And then here's Alabama, and it borders both Georgia and Florida, so it'd have to be a different color. And then we come up to Tennessee, and it can't be colors 1 or 3 because it borders Georgia and Alabama, but it could be color 2. And then over here, this could be color 3. And over here could be color 1 again, and so on. And you might just experiment by trying to fill in some surrounding states, pausing the video and seeing what you can do. What does this have to do with graph theory? Well, first of all, let's convert the map to a graph as follows. Here's a blow-up of part of the United States, Montana, and the states surrounding it. And let's simply put a dot or a vertex in each of the states. You can imagine it being the capital city, for example. And then we're going to connect vertices with edges if and only if those two states for those vertices share a geographical border. So for example, Idaho and Montana obviously have a geographical boundary that they share. And so let's connect the vertex for Idaho with the vertex for Montana with an edge. On the other hand, Idaho here and North Dakota here do not share a geographical boundary, and so we will not put an edge directly between these two vertices. So let's go ahead and add the other edges that we need between Montana and North Dakota, North Dakota and South Dakota, South Dakota and Wyoming, Wyoming and Idaho, Wyoming and Montana. And here's just a little edge, geographical boundary that's shared, so Montana and South Dakota. And I believe that's it. Notice that Wyoming and North Dakota don't share a boundary. Once we've done that, we've actually captured all of the relevant information for this question. Let's then take these relatively complicated geographical boundaries and just dissolve them. And here's the information that we need to do the graph. We now want to find the minimum number of colors to color these vertices. There's one vertex for each state, so that no two vertices sharing an edge have the same color. Remember, this was the vertex for Idaho. This was the vertex for Montana. These two vertices are connected by an edge because Idaho and Montana share a geographical border, and so those two states should not be the same color. So on our graph now, this vertex and this vertex should not have the same color. And so let's try here. Color number 1. This could be color number 2. If I come down here, this was actually Wyoming. That can't be either 1 or 2, so that needs to be a third color. Then I come back over here, and that can't be 2 or 3, but it could be 1. Notice I could use another color like 4, but I'm trying to find the minimum number of colors. So I'll never introduce an additional color unless I need it. Then I come back up here, and this could be color number 3. So I can color just this little subsection with 3 colors. But back on the big graph, how did you do, if you tried this, how did you do for the entire graph? I started down here. Let me go over here to Nevada just because I know how this is going to work out. Let's let Nevada be color number 1, and California has to be different, color number 2, and then Oregon has to be still different, so color number 3. Then I could use color number 2 again for Idaho, and color number 3 for Utah. And now I come down here to Arizona. Notice it can't be color number 1, can't be color number 2, can't be color number 3, has to be color number 4. So I'd be very surprised and suspicious if you managed to color the United States map with less than 4 colors. And I think if you work hard enough at it, you can do it with 4 colors. In fact, I know that you can do it with 4 colors. Because in 1976, the so-called 4-color theorem was proved that says any map can be colored using at most 4 colors, and it turns out the map of the United States does need exactly 4 colors. Perhaps another map, like the little map just surrounding the state of Montana, could be colored with 3 colors, but at most a map can be colored with 4 colors. This is not that long ago. I mean, it was probably before you were born, but in terms of mathematics that's been around for thousands of years, 1976 is just a few decades ago. So I wanted to include this to help you see that mathematics is not something that was all settled upon hundreds or thousands of years ago. People are still doing mathematics research all the time and making new and important discoveries. I also wanted to point out this particular theorem because it was the first mathematical proof to be done using a computer in an indispensable way. And let me explain a little bit why that is significant. Mathematicians like to prove things. We tend not to take things on face value and just say, oh, that looks right. I believe that. No, you're supposed to construct a mathematical proof using careful logic and saying, because of this, then this is true, and because of this, then this is true, and because of this, then this is true. You may have done that in a geometry class, for example. We're not going to do that in this particular course, but it is an important part of the work of a mathematician. Well, this 4-color theorem was actually a conjecture made in the 1800s, around 1850 or so. A mathematician proposed that any map could be colored with 4 colors, but he wasn't able to prove that. It just seemed right. And so many mathematicians after that tried to prove the 4-color theorem with rigorous logic. But it was a very complicated problem. And so nobody was able to do that until 1976. And these two gentlemen at the University of Illinois were also not able to do the proof, at least by hand. What they did was succeed in breaking down the problem into an enormous number of special cases, thousands of them in fact. And humans can't keep track of thousands of different detailed cases like this. So they were able to put the special cases on a computer and have a program run checks for them. And at the end, because the computer did all those possible checks very fast, like computers are able to do, the problem was considered proved, at least by them. But then other mathematicians said, wait a minute, the computer did this, and perhaps you made a mistake in programming your computer. You see, when proofs are done by hand, other mathematicians check them. They read through them and say, oh yeah, that's right, that's right, that's right. And finally they sign off, and when a few people have agreed that a proof is correct, then it's considered to be so. Well, nobody could really check this, because even if you have the computer program in hand, you can't necessarily walk through the same sequence of steps that the computer did. And so this was a big deal for mathematicians. It's a new way of thinking. By now, 1976 has been several decades ago, by now most mathematicians agree that this type of proof is okay. Important point to make in terms of the history of math. Let's get back to graph coloring. Terminology, chromatic number. Let's say the chromatic number is the minimum number of colors needed to color a particular graph. So example, here's a graph. How many different colors do you need to color this graph? Well, let's see. Let's make this color number 1, 2, and then whenever I can, I'm going to reuse colors I've already done. So 1, 2, 2, 1, 2, 1. Oh, I think I see a pattern going on here. 1, 2, 1, 2. And notice that no two adjacent vertices are the same color. So even though this graph has quite a few vertices, in fact, only 2 colors are needed, and this graph has chromatic number 2. How about this one? You might want to pause the video and think about this a bit. Let's see, 1, 2, and then down here I would need a third color since this vertex is connected to the 2 that I've already done, so at least 3. Then I can come back over here and I could make this 1 or 3. Let's go for 3. This could be 1. This could be 1. I can reuse 2. Over here I could reuse 2 and 1, 2, 3, and 1. No two adjacent vertices the same color. The chromatic number of this graph is 3. I hope you took my advice to pause the video and try to do this yourself. If you had made a different choice, I believe right here and right here, like you had called this one 1 and vertex 1, then when you had gotten down here, you would have thought that you needed another color, color 4. And so this is a non-trivial task. It is possible to make choices that are not the best ones. Not that they're wrong, but they're not the best ones. And so when you get done, you don't have as good of a solution in terms of the minimal number of colors as could possibly be done. And so it's starting to sound like either we'll have to do this problem brute force or find a clever algorithm that tells us how to go about getting the best answer, because just walking through it following your nose isn't necessarily guaranteed to get to the minimal number of colors. Here's another example. What's the chromatic number of the complete graph with 5 vertices? From the reading in the text, perhaps you remember a complete graph is one in which every pair of vertices is connected by an edge. And so if I have 5 vertices, let's say arrange them in a pentagon shape, then a complete graph has edges between all pairs of vertices. And so it looks like this. There's the outer ring, but then there's a connection here, and here, and here, and here, and here. Notice that there are just 5 vertices. So you see these edges crossing in the interior, but that's just a remnant of the drawing. There is no vertex here in the interior. Okay, what about coloring this? Well, we'll need one color, a second color. Come down here. It's connected to both 1 and 2, so it needs to be a third color. But wait a minute, every vertex is connected to every other vertex. And so if you think about it, no 2 vertices in this graph can have the same color because every pair of vertices shares an edge. They're adjacent to each other. And so all I can do is just keep adding colors as I go. So a complete graph has a chromatic number exactly the same as the number of vertices. We saw earlier examples of graphs that were not complete, that had some edges missing, and in that case the chromatic number might be much smaller than the number of vertices. This is graph coloring. Let's go back to the problem posed at the beginning, this business of conflict resolution, building schedules. Suppose the university wants to schedule final exams for the courses French, Math, History, Philosophy, English, Italian, Spanish, and Chemistry. Some students are in more than one course, and our goal is to schedule the exams in as few time periods as possible, but avoiding conflicts. I assume that you're like most of us, you can't be in 2 places at the same time, taking more than one exam at the same time. So if, for example, there is a student taking both French and Math, then the final exams for those 2 classes can't be at the same time. Of course, we want to schedule the exams in as few time periods as possible to get the examination schedule done as soon as possible. If we can fit the exams into 3 days or 4 days, that's better than spreading them out over 6 or 7 or 8 days. I would assume you'd agree with that. Let's suppose that the particular example has students as follows. An X in the table indicates that the courses in that row and that column have a student in common. So for example, there is an X here. That means yes, there is at least one student taking French and mathematics, and so that exam can't be at the same, those exams can't be at the same time. On the other hand, nobody is taking both French and history, so the French final and the history final could happen at the same time. What do these 2 questions have to do with each other? Conflict resolution and graph coloring. Let's take this table of conflicts, essentially, and convert it to a graph as follows. What I want to do is turn the conflict resolution problem into a graph coloring problem. Let's have the vertices represent courses. So there were classes French, Math, History, Philosophy, and so on. We'll build a graph in which there's a French vertex, a Math vertex, a History vertex, and so on. Let's have an edge represent, or edges represent, students in common. We're going to connect vertices, in other words, connect courses by an edge if those two courses have at least one student in common. Remember, that's pretty much how graph coloring worked. In fact, exactly how graph coloring worked. And then what are the colors themselves? We were trying to minimize the number of colors, 1, 2, 3, and so on. In the conflict resolution problem, we're trying to minimize the examination periods. And so colors represent the time periods that are available to have exams in. Now, what we're going to do, as I said, is take this tabular information and draw a corresponding graph for it. To get us started, I've actually arranged the vertices here. So remember, there was a French course, so now there's an F vertex. There was a math course, there's an M vertex. There's a history course, there's an H vertex. And now let's add edges as needed. If you look back at the table, if you have a printout, there was a student taking both math and French, and so there should be an edge joining those vertices. There was no student taking French and history, so there will not be an edge between these two vertices. And now I'm kind of working on the French, and then I'll go to the math and history and so on in that order. There was a student taking both French and philosophy. Connect those. French and English, yes, connect those. French and Italian, yes, connect those. French and Spanish, no. French and chemistry, yes. Let's go on to math. Math and French. There was a student in common, but I've already drawn the edge for that. Math and English, yes. Math and Italian, yes. Let's see, what else? I think that's it for math. Let's go on to history. History and Italian, yes. History and Spanish, and history and chemistry. How about philosophy? Philosophy and French, we've already drawn that. And philosophy and chemistry. By the way, of course there's a student taking both philosophy and philosophy, but there's no need for me to try to draw an edge there. The starting and finishing vertices would be the same, and there's no need to keep track of that information. There's no consequence to a conflict between philosophy and philosophy. It's the same class. On to English. English and French. We already have that edge. English and math, yes. English and Italian. On to Italian. Italian and French, already there. Italian and math, already there. Italian and history, already there. Italian and English, already there. Italian and Spanish. On to Spanish. Spanish and history, yes. Spanish and Italian, yes. And finally, chemistry. Chemistry and French, already there. Chemistry and history, already there. Chemistry and philosophy, already there. And I believe that's it. So this graph, again, corresponds to, has the same information as this table of conflicts between the classes. And so now to find a final exam schedule without conflicts for this table is the same question as finding a coloring for this graph. In fact, finding a minimal coloring, finding a coloring using the smallest number of colors or exam time periods as possible. Okay, let's see what happens. If I start here at chemistry, for example, that could be color 1. French needs to be a different color. Philosophy needs to be at still a different color, so already I see that at least 3 colors will be needed. Then I could come over here to math. That could be period number 1, and English could be period number 3, and history could be period number 3. Spanish could be period number 1, and we're left with Italian, which can't be period number 1, 2, or 3. So it looks like I'm going to need a 4th color here. Am I sure about that? Well, not positive. To be sure, I probably want to go back and try some different choices, starting out differently at a different vertex, and every time I had a choice, maybe think about what would have happened if I had gone the other way. Would it be possible to get down to 3 colors? I'm positive it can't be done in less than 3 colors. In fact, if you try hard enough, I think you'll convince yourself that you actually do need 4 colors for this particular graph. The chromatic number of this graph is 4. Here is such a coloring, and then to translate this result back into the language of the original problem, what exams should be given during which periods? Remember, the numbers corresponded to the periods, and so color number 1 corresponds to exam period 1. That was chemistry and math and Spanish. Can all happen at the same time. So I recommend to this registrar that the first period have chemistry, math, and Spanish exams. The second period can have the French exam. Were there any other 2s? That's all we use, 2, 4. 3 could be philosophy, history, and English. And then period 4 we needed for the Italian exam. Okay, this is one possibility. 4 periods, no student conflicts. And with the information that we have, this is just as good as any other answer. It may be that somebody would say, oh, well, wait a minute. If we have 3 periods here, 3 exams taking place in period 1 and only 1 test taking place in period 2, maybe I'd want to balance that a little bit and try to find a coloring that used the same color, each color about the same number of times. But that's beyond the scope of the information we were given for this problem. So let's leave this example. Here's another one. You might want to pause the video and work this one out. It's very similar to the example that we just did. In fact, the context is the same, different classes trying to schedule final exams, only the conflict table is a little bit different. I'll go ahead and do this example. Notice that this example might be just a little bit harder than the previous one, not because it is, but because I haven't given you as much information. On the previous graph, I actually drew the vertices in place, and then you connected, or we together connected the vertices with edges as appropriate. Here, I'm not placing the vertices, and so you might want to play around with it just a little bit to try to draw the vertices in positions so that the graph appears as simple as possible. It's not necessary to avoid edges crossing each other, but in terms of being able to do the coloring easily and to see what's going on, it's very helpful if the graph is in as simple a form as possible. And so here would be one possibility. If I put history here, and math here, and Italian here, and English here, then down here chemistry, philosophy, French, and then Spanish can go anywhere. Why did I do it that way? If I look back here, I notice that philosophy and chemistry and French, for example, um, have students in common, and so it might make sense to group those together. Whereas Spanish had no students in common with any other class, and so it didn't matter so much where those went. It's not wrong to put the vertices somewhere else, not at all. And as you're doing this problem on your own, you probably would have put them in somewhat different positions. But think a little bit before you start drawing the graph, just to get the vertices appropriately arranged so that vertices that share an edge tend to be nearby. Okay, there is a student in both history and math, in both math and Italian, in both Italian and English. There is at least one student in common between chemistry and philosophy, and between philosophy and French, and then Spanish has no student in common with any other. Let's do a coloring. Well, this one's pretty friendly. If I make this color number 1, then color number 2, and because this is a chain structure with no branches, I can just go back to color number 1 and color number 2. Now this is completely disconnected, so I can start however I want. Color number 1, 2, 1, and I could make this either 1 or 2. Okay, there's a coloring with only 2 colors. Clearly one color, just having one color is not possible. So I think I've done the best possible I can do here with 2 colors. And then in terms of what happens in period number 1, we can have history, Italian, chemistry, and French. And in period number 2, math, English, philosophy, and Spanish. And period number 3 is actually not needed. Okay, that finishes the second example. So you should be able to do problems like this, taking the table and converting to a graph, doing the coloring, or perhaps vice versa, taking a graph and translating it back into a table form. This finishes actually the first module. The unifying mathematical theme of the first module was graphs with vertices and edges. And we looked at 5 categories of problems: Euler circuits, of which the Chinese postman problem was closely related; Hamiltonian circuits, the traveling salesman problem was closely related to that; spanning trees, task scheduling, and now graph coloring. And as we went along, I pointed out that some of these problems are easy for a computer, some are hard. Which problems have efficient computer algorithms to solve them and therefore are easy? Euler circuits, yes. Hamiltonian circuits, no. Spanning trees, yes. Task scheduling, no. And now graph coloring, we haven't given the answer for this. It turns out that this is a hard problem as well. So we've considered a couple of types of questions that are easy to do on a computer. Very large problems for spanning trees and Euler circuits can be done on a computer. But the other 3 types cannot be done exactly on a computer for very large problems. And that finishes the first unit, and this will be the content of the first exam, the material up until now.